you very much for joining us on AU Manufacturing Conversations.
Thank you. Thank you.
So first question, as always, is how did you get here and what do you make?
Excellent. I might start. My name is Thomas Romeijn. I'm with Mineral Technologies, have been for 12 years. Born and raised in the Netherlands and had a chance to study at 3 universities, which the last collaboration is with the University of Technology, Sydney. And that's relating to the project we've got going at the moment, together with IMCSC, on the 3D printing of a key piece of mineral separation equipment.
My name's Dr. Michael Behrens. I'm a researcher with UTS Rapido. We're an R&D engineering consultancy embedded within the University of Technology, Sydney. And we have been collaborating with Thomas and Mineral Technologies on this project as well. I have been with the University of Technology for quite some time. I did my undergrad and my postgrad, and now I work there, so I have a very defined daily commute. But I love working in such a innovative and just everything's interesting and new all the time, so I love my job.
And so that's a very brief introduction. Both of you guys have quite long backgrounds, and I'm sure we could take up all day, but we don't have all day, so let's perhaps go to the next question. Tell me about the project you're doing and how what you're trying to do with 3D printing is different to the traditional manufacturing of separation spirals.
Yeah, good question. So separation spirals is one of our key products. It's a really simple piece of equipment. Imagine a helical shape, a meter wide, 2 meters high. And clients love it because if you pour a slurry in the top, it spins around and we've got separation at the bottom. And that's exactly what we're trying to do at Mineral Technologies, separate stuff from other stuff. And this spiral has been around probably since the, I would say, 1950s in one form or another. It was cast iron back in the day, bolted together. Innovation at that point in time was, let's go and try this new fiberglass material. So that happened, and it was very successful throughout the years. And now we're looking at the next step. Can we improve upon fiberglass through the use of 3D printing? And this is what this project is about. Can we take the next step in spiral innovation?
And so tell me why you can do better than fiberglass. You guys are world leaders, as I understand it, and have a fairly healthy command of the market for these. Why did you need to do something new? What's the purpose of what you're developing?
There's probably three aspects there. Firstly, use of fiberglass has some inherent hazards, manual lifting, and we need full PPE, and that's all well and good and under control. But if we could eliminate those hazards, that would be even better. So one is personnel safety in the manufacturing space, which is important to the business. The second aspect is that 3D printing gives you way more flexibility. I think a lot of people know about 3D printing and know you can basically create any shape you want. We're applying that to mineral separation spirals with the aim to improve our prototyping cycle. So currently, fiberglass new model of a spiral would require a new mold, a new plug, which has to be manufactured. It has to be brought back into the factory, and then only then would you have a new prototype. Where 3D printing would just allow you to, almost with the push of a button, change your shape, and off the printer goes. So that's the second aspect. And then finally, customization of these spirals. We have a large range of spirals for different applications, and clients come to us and say, Mineral Technologies, please tell us what would be the best model for our ore composite, right, our ore body. And we go through a testing cycle, and we recommend a model to be best used in that case. But how good would it be if you can customize your spiral to the client's ore body? And we think that is the end goal of this project, that we can actually provide a customized solution to get your best possible mineral separation efficiency.
Right, I understand it, and I couldn't understand it in depth because I'm not a mathematician or anything else, but you made it sound very simple just then. Slurry goes in, separated stuff comes out. There's a lot of physics and a lot of calculation involved, isn't there?
That's right, exactly right. It's a really interesting aspect because it's a dead simple shape. It's really a helical shape with a special curve on its cross-section. But to understand the separation processes has been a topic of research for many years now. Myself being heavily involved in it. And we're currently using fluid flow simulation to understand what actually happens inside that spiral and how does the particles segregate as they flow down. And that's an ongoing thing. So we at Mineral Technologies are really focusing on simulating and understanding that separation behavior on first principles to be used to help the clients again. If the client has a certain particle distribution, the idea is that we input that in our software and actually get an idea of separation efficiency, use that to tweak the cross-section and print and test.
You mentioned print just then. There are a lot of different kinds of 3D printing, but the models out there on the floor that we saw earlier appear to be FDM printed. Why did you go with that particular 3D printing method?
Certainly I can answer that question. Early on in the project we did a complete review of all of the printing technologies which were available at the time, and FDM came up as the most ideal solution for this particular problem. It's readily available, it's well understood, and it does the job we need. To your question about the strength of the materials, that was another aspect of the research. We did a full analysis on the strength of the printed parts in various different orientations. We looked at the abrasion resistance of the materials, all to make sure that whatever we produce at the end will be of equivalent performance or better than the existing materials used in the current spirals.
And is there a specially developed resin of some kind? Did you develop that in-house?
No, we haven't developed anything particularly bespoke for this. We've looked at the commercially available off-the-shelf materials. Did look at a wide range of different materials, and we picked the ones which are optimal. And yeah, and as I said before, we've done a testing process to verify through physical testing that it's not just looking at a data sheet. We've done the tests, we've run the rigs, and we've got data to back up those decisions.
Thomas, this is a PhD problem for you.
Yes.
Tell me exactly what your PhD involved and how it relates to what we're talking about now.
Yes, this was the last 4 years of my life. The way, basically, we're currently making these spirals out of fiberglass, and that's got certain material properties. And we need to maintain this shape throughout our promised surface life, right? So these spirals have 10-year surface life, and the goal, obviously, is to have an equivalent design, but 3D printed. So the client needs to be confident that it can still reach that 10-year surface life. So we then have the problem of we're changing away from fiberglass to a new 3D printable material, but it's different material properties. And if you're designing a new product, you need to look at three aspects. You need to look at your geometry, right? I'm sitting on a chair at the moment. If I want to redesign this chair, I need to look at, okay, what are my key aspects of the geometry? Well, it's probably something to sit on, and it's probably something to lean against. Same with a spiral. What key geometry do we need to maintain in the 3D printed equivalent? Then forces. I'm weighing a certain amount, probably more than I like, but it's being applied to this chair. What are my forces on the spiral of this slurry spinning around, which is where our simulation of flow and particles comes in. That will tell me the loads on the structure. And finally, extensive material testing. So this is a plastic chair. If I'm going to a wooden chair, I need to know what are the material properties of that wood, and same with the spirals. We've got a new material, so we need to know the material properties of that. And if you combine those three, if you combine the geometry, the loads, and a new material, that's all the input you need to come up with an equivalent design. So that was the focus. Getting those three topics, nail them down, and that would set us up to take the next step, actually change the geometry to something you can 3D print.
Challenges across this project. It's been running a while. Tell me, what are some things you came up against and how you dealt with them, if you're able to?
Yes. The load scenario was the specific, very challenging aspect, actually. There's been a lot of research on the flow and the separation behavior of mineral separation spirals. My approach was to apply fluid flow simulation, but you have to imagine that a fluid flow simulation package is basically a collection of mathematical models that have been calibrated on simple flow scenarios. Imagine a flow over a weir and how that turbulent behavior is captured. That's a simple case study, but it's calibrated the model to that scenario. Now, the flow software enables you to pick certain flow models or lift models or drag laws, etc. But getting them to work together is a real challenge. And the essential in fluid flow simulation is the validation. So if you pick a range of models, it'll give you an outcome no matter what. But actually getting that outcome to match reality is what the challenge is. And we've done that for simple water flow on one of these spirals. And it's currently being done for a particle flow, so a slurry flow. Yep. And getting that interaction between the particles and the wall and the flow is a challenge.
And Michael, do you have anything to add, perhaps on the 3D printing side?
Yeah, from the actual machine build side, it's an incredibly complex machine that we've created here, and it's one of the big challenges is the fact that it's not a standard 3D printer. It's customized specifically for creating these particular parts, and that lets us increase efficiency and reduce costs, but it means we can't use any of the standard off-the-shelf slicers, for example. So we've had to roll our own custom slicer for this, so it all operates in polar coordinates, and with the machine's got 14 degrees of freedom, so there's a lot of moving parts that we can choose different ways of orienting a machine for a particular run in the print, and then finding the optimal arrangement of those so that we can do it in a minimal amount of time, make sure that the two robots don't crash into each other, that they minimize the reconfigurations as we go, and then we have to make sure that we manage the shrinkage of the part so that it stays the right shape as we print. There's a lot of technical problems there. That sounds simple when you kind of like wave a hand over it and go, yeah, we'll just 3D print this thing. And then when you get to the nitty gritty of it, there's a lot of complex problems that, like, a problem pops up, and then we find a solution. And another problem pops up, and we find a solution for that one. That's the big process of engineering development for me.
Right. And key to mention there, I think, is that it's printed without a support structure, which is quite unheard of in 3D printing. Because normally, if you have, imagine a helix, so it overhangs quite a bit. So normally you would have a support structure, and for a helix that could become very complex. But in this case, Michael managed to find a way to not have that there. So that's quite a...
It was a bit of a mad idea right at the beginning. We just thought, why don't we just start with the middle pole for this, and then we'll just print sideways. It's like lathing something in reverse. And like we looked around, and no one's really ever tried to do something like this, and it's like, is it gonna just completely fall apart? But we knocked up a bench prototype just to prove the concept, and that's what you can see down on the table. And it works beautifully. Yeah. And it looks like an impossible shape to 3D print, but it just comes out of the printer ready to go, which is wonderful.
Right, and so that's a hell of an innovation. I'd like to know, on the topic of innovation, what's the definition that you guys give to that word?
Well, actually, I might quote David Shooter just now. He had a very inspiring talk, and he mentioned innovation and invention, which I found it sort of just clicked in my brain that there's plenty of inventions, but an invention for me would be just something that's new and exciting, but not practical, can't be practically applied easily enough. And innovation to me is forming that practical link to what you do at the moment. So this is innovation to me, where you have a spiral and a new way of manufacturing. And that would be the definition for me, is a practical way of doing something new.
Nice.
Yeah, I have a very similar definition for myself. It's finding a new use for things that already exist. So invention is creating something completely new, but innovation is going, there's this thing that gets used in this way, why don't I try using it in this other way? And a lot of the time you can get some really big gains out of doing that process.
Tell me about the stage of readiness you're at. Is it about time to start using these in the field?
Probably as we speak. I've got a team up in Queensland. We're doing final commissioning and final tuning of our big commercial printer. It's the size of a shipping container. And so we are printing spirals at the moment. I think that it will be a little while, but probably by the end of the year we should be able to have spirals that we can put in the lab, and we can actually run slurries over them and test their effectiveness. And then in the very near future, we should be able to see spirals out in the field.
Yep.
So would you be selling the spirals themselves or machines to make them on site?
Well, the machine would be property of Mineral Technologies,
Right.
but the business case there is that currently we manufacture spirals at 2 locations worldwide. We put these spirals in a shipping container and send them all over the world. The problem with that is they don't stack particularly well. So what I always like to say is that we're basically shipping a whole heap of air around the world, which is not beneficial to anyone. So it would make far more sense to actually ship the printer and get these to close to a mine site and actually print the spirals right there and then. And then that printer would fit back into its container and ship to the next spot. So we basically are looking at a series of printers basically traveling the world constantly and printing spirals where they're needed, instead of relying on 2 hubs and distributed from there worldwide.
So you'd have sort of a servitized model where you send out the spiral machine, you fix it if something goes wrong, and the customer uses it as they see appropriate.
No, there would be a service provider, so a Mineral Technologies employee or team would follow this printer around, and they would manufacture the spirals, so we still have the quality control we would like, and any issues would be resolved right there and then. And then that team would follow the printer to the next location and the next location.
So that's pretty much all we have time for, though there is time for one more comment or perhaps thing to plug if you'd like to do either of those things.
Well, I would just refer to the Mineral Technologies business. We've been around for 80 years, starting on the Gold Coast, one of the leaders in the field, and I think this new technology proves that very well. We're trying to innovate and we're trying to improve the way we do things to get the clients their best outcome, because the ores back in the day, I looked it up, and they were shoveling our ilmenite off the beach at 90% grade, which is absolutely unheard of these days. And we're looking at a percentage of below 1% in your ore body. So getting a customized solution to get your best outcomes is a big thing for the industry, I would say.
Michael?
Yeah, I'd definitely say if you're looking for doing some unique and groundbreaking technology development, definitely come and check out UTS Rapido. We're a relatively new organisation or new unit with the University of Technology. We've been around for about 6 years now, and we're a bit of an experiment by the university for looking for better ways to leverage the skills and resources in the university to give business outcomes to industry partners. I'm not involved with teaching. I don't have to publish papers. My entire purpose is to get business value for our clients. So we have strength in mechatronics, in software development, so we've got algorithms and web apps and machine vision, to name a few, and we also do some stuff in the user experience space, so making sure what's created is useful in the end.
Yeah, I can actually testify to that, because we looked at collaborations earlier, but the good thing with the Rapido team is that they're really practically minded, and coming from the industry, there's always this barrier between the theoretical research and the practical application in industry. The Rapido team really bridged that gap really well.
Thank you, Thomas.
Thomas and Michael, it was a pleasure to speak to you both. Thank you for joining us here on A Manufacturing Conversations.
No worries. It's been a pleasure.